So this situation, electron in a region where there's an electric field experiences a relatively small force magnitude, 10 to the minus 16. That's what, 10,000th, 1/10,000th of a trillionth. So it's an incredibly small amount of force, but an electron is also incredibly small. So the equation that we're going to use is force equals QE. Necessarily, forces are vector quantities, and electric fields are too. Since we're talking about magnitude, technically we should do our math that way, I guess. That would be the by-the-book legit way to write it. But if you were to write without the vector symbol, a lot of textbooks will, that's assume that you're talking magnitude. And I think that is less troublesome and tedious to write it that way, so I'm going to do it. Now, what we want here is the electric field. So fields, electric fields, or any field is always force per unit, whatever matters in that field. And so we were told, this is super simple, that we had 3.8 times 10 to the minus 16 newtons. And it's an electron, which has an elementary unit of charge. And as we learned Monday, it has no constituent parts. Protons and neutrons do, and as far as we know, electrons do not. And so the magnitude of this electric field, simple calculation, you end up getting 2375 newtons per coulomb, which, by the way, is the same as 2375 volts per meter. And in fact, that's what you'll see in the Charges and Fields lab. When you do the electric field sensor, a little yellow dot, it'll give you an answer in volts per meter. It's the same thing as newtons per coulomb. And that's probably worked out in the book somewhere. I'll double check on that. So simple, easy peasy question. On to the next. I also tried to number these slides in the future. I forgot to do that. Have a number on screen. But here we have this electric field at a location's measured to be 0, negative 280, so it's all y in the negative downward direction if you're going to do a standard system. What force would a positron, and so positrons are positive electrons, if you will, they're the antiparticle, and so force is just QE, like we said before. So we're still in Simpleville. So a positron would have that elementary charge, it'd be positive, and then this vector 0, negative 280, 0 at newtons per coulomb. So you do that multiplying out. Your x component's going to stay 0. This y component will reduce in magnitude a bit because of that charge. So 4.48 times 10 to the minus 17. And then your z was still 0, and it's that number of newtons. Now, from a magnitude standpoint, now I guess we should be careful because of what we wrote here. Technically, I'm dealing with the vector. All right, so I have that right there. If I were to write the magnitude of that vector, I could, since it's a single, everything is one non-zero component. All right, so if I square every component, add them and square root it, I'm just going to get that middle component, that y component back, and its magnitude would end up being 4.48 times 10 to the minus 17th newtons if it was just asking for a magnitude. But it asked for the force, and it gave you vector inputs, so it's expecting vector outputs. But this right here is certainly, as long as you recognize it's the magnitude, but the answer that it was looking for, it was looking for a vector, and that is a vector because it's got parts. magnitude and direction. All right, so easy peasy on that one too. We're working our way up to the more complicated ones. Particle figure below is a proton, so that Q2 is a proton in the electric field. E1 has this value. It's got two non-zero components, so we're going to have to deal with Pythagorean, magnitude computation, unless we are entering this on a calculator or computer in vector form, and then you can just hit buttons. I think one of my trinket calculators on my website, and you might still have one, would do the vector math for you, so feel free to use that. But the equation, again, F equals QE, and we're dealing with vectors, and so we need to pay attention to that. And so we're going to have a positive 1.602 times 10 to the minus 19 coulombs. That's the proton going there. And then this E vector, 2 times 10 to the fourth, 2 times 10 to the fourth, 0, and then that was newtons per coulomb. So we plug and chug that stuff. This is still easy peasy. Multiply a scalar into the components of a vector. No big deal. 3.2 times 10 to the minus 17, 15. Really small number of newtons. If we wanted to compute that magnitude, we'd have to square both things, add them, square root it. They were asked for that. We also know it's at 45 since the x and the y components are the same. So it would be easy to answer those kinds of questions if they're asked. They were not. All right, a couple of slides here. This is one of them. I think there's 3 or 4 where I just give you the answer since it's a narrative answer, and I don't want you to bother with having to scribble that out, and I don't want to scribble it out either. It's hard enough doing the equations right. So here in this region of space, what's here? If all the electric field lines are pointing inward, it has to be a negative charge. If they were pointing outward, it would be a positive charge. It's that simple. Part B, what is the direction of the electric force on a particle whose charge is negative? And in fact, we could just say negative, all right? So if it's negative, then it's going to be repelled by whatever's here. Of course, what's here, there's a negative charge of some amount here. Okay? That means if I put a negative charge here, it's going to be pushed away, down and to the left, and along this line. It's going to be pushed along that line. So some of these are just factoids, and so I do base test material on these things as well, so it pays to take notes. All right, part C here. I think we get to do some math. What is the unit vector in the direction of E at this location? Okay, so it's been a while since we've done this, and I think we switched to just letting a computer do it. But mathematically speaking, that is how you compute a unit vector. And the reason for that is the definition of a vector is something with magnitude and direction. So I was saying those things as I wrote it. That is, all vectors have that property, and we use those kinds of notations here. So, what's the magnitude going to be? Well, we'll just kind of write it in place here. So E is just going to be this 2,000, 0. Newtons per coulomb. And then you're going to have 2,000 squared plus 2,000 squared plus 0 squared, as if we need to write it. Also some number of newtons per coulomb. That's why unit vectors have no units. Bad name. And we're going to get hopefully you recognize, oh, that's just root 2 over 2, or 45 degrees, because that must be what we're dealing with, in this frame here, just as much up as it is out, or across rather. So there's our unit vector in 45 degree. Those are cosines. Remember, unit vectors, those decimals are the cosine of some angle, and they would technically be, give me my pen back. The x is going to be, I'll call it theta x, call this theta y, and that theta z, meaning those are the cosines of the angle between the vector and each axis, theta x, theta y, theta z. And so you can always get those angles. You can convert those to polar, spherical, etc. in those ways. But inevitably, you'll just get a computer to do that for you, which I highly recommend. I think you can do this in math way. Desmos, I can't remember if Desmos does it or not. There's a number of options out there that will do this. Your calculators, if you have a graphing calculator, it'll do vectors. And it'll do the units. I think they call it norm. Magnitude is called mag usually, kind of like in Python. All right. Continuing on with this, what's the electric force on this minus 7 times 10 to the minus 9th charge? So make sure if you have the old version that there's a minus 7 or a negative on this charge value. I think this is the first slide with a copy error. And so here we go. So force, again, just QE. And so we're going to have negative 7 times 10 to the minus 9th coulombs. So that's negative 7 nanocoulombs. 10 to the minus 9th is a billionth. And then this vector, that number of newtons per coulomb. And so that means the force on this, negative 1.4 times 10 to the minus 5th, repeated, and a 0 there, and that number of newtons. Again, if you wanted the magnitude, sum of squares, square rooted. All right. This kind of just an answer given away. I think it's the end of this multi-part problem. There's 24 pages or 25 pages, and like 3 of the problems take 4 or 5 pages because they have parts. So it's probably 8 problems. I can't remember how many problems it is total. In this picture here, same region as before. What is the unit vector in the direction of the electric force? Well, it has to be in the direct, so we know that the force is pointing that way. We did that in the beginning. And so if the unit vector of the field was pointing that way, then the unit vector of the force has to point the other way because an opposite charge. If it were a same charge, negative to negative. If it were positive, then they would have the exact same unit vector. So that's something to think about. If we do the math correctly, then the math and the directions are all wrapped up together. Otherwise, you have to, this is interesting here, that little caret, little typo, that should just be, let's do this. There. Can cheat. Little typos there. Okay. So make sure that caret shouldn't be there. Correct that to be the vector. Well, that caret, I'm sorry. Caret needed to be over it, not next to it. So, need more coffee. All right. Here is another problem where I needed to have a narrative that you could refer to when you look at it again without having to write all of this. So let's think about the situation, and then we'll get to the math part of this, which involves some connection back to first semester. So electrons in space, it's accelerating in the positive z direction, which would be out from the screen at you if we were using that. Has a really large acceleration, 10 to the 16 meters per second every second. That would mean, if it were physically possible, in a fraction of a second, it's past the speed of light. Obviously, you can't do that. The fastest we can get an electron to is at the Large Hadron Collider in Switzerland, at CERN, and we get it just under 3 meters per second, shy of the speed of light. It takes an enormous amount of energy to get that beam of electrons that fast. We'd have to make that accelerator bigger than the Earth just to maybe move it a meter per second closer. It's insane. And so they are working on some different ways of doing particle accelerators, even tabletop versions that might do stuff like that. It's weird stuff. So anyways, so particle will accelerate in the direction of the net force on the particle. That's first semester Newtonian stuff. So we must have that going for us. And so one way to characterize that is you can say that the net force is dp dt. Now that's the same thing as delta p delta t, basically. If you go back to our first semester, those collisions, and we developed the impulse momentum theorem. So F net times delta t would equal the change in momentum, and that's just the impulse momentum theorem. And so this is the way Newton wrote his second law. MA is the way we kind of cheat these days. And so it must be whatever force is on the particles in the z direction, and that net force has to equal the dp dt. That's just sort of fact, all right? And we also have, and so there'll be some math to do there. We also, I'm gonna get rid of that right there, clear up some space. And to be clear, the force that's exerted by the electric field is going to be equal to MA, okay? Because there's nothing else. It's a universe with just this field. And so the mass of that electron, it's going to be, it has an acceleration, and so whatever the force of the electric field is on the particle, that is also, it's computable by a QE, but it's also going to be equal to mass times acceleration, because that is the net force in this case, all right? So we can use all of that, and that's what that red, blue, green paragraphs or sentences are for. And so if we kind of go from that, what we can do is the mass of an electron, so I'll just call that Fe there, or E field, is really small, 9.31, or no, 9.1 times 10 to the minus 31 kilograms. And that acceleration that we were given, we were in the z direction, so we should write it this way. I'm actually going to change it to newtons per kilogram because those are the same thing. Newtons per kilogram and meters per second squared are the same thing. They just connote a different idea. Since we're talking about force, I want to have force units. And so this E field force, you compute all that out, you're going to get 0, 0, and 1.46 times 10 to the minus 14 newtons. All right. So now we have that E field force, and so we can take the definition of an electric field, which is force per unit charge. And since we're still dealing with vectors, we'll do that. And I'll just squiggle that for what's right above it. And that charge is an electron, so 1.602 times 10 to the minus 19 coulombs. And that means that our electric field in the final analysis is just 0, 0, and negative 9.13 times 10 to the 4th newtons per coulomb. So, simple math, how will this work out in reality for, say, someone's career field? So say you're an engineer, like an electrical engineer or something like that, working on antenna design, which means you're dealing with electric fields. You need to know the shape of the space near that antenna. If it's transmitting, it's going to produce something. If it's receiving, it needs to fit into the field and or whatever. And so this math would be part of, people be writing code and then computing these in matrices and things like that. And so sensory inputs will be putting in certain values to this. And so somebody's going to do this computation, or you're going to reuse somebody else's code. That's just the way that this is going to go. And if you are modifying stuff, you need to know what it is you're modifying, which is why you take courses like these. All right, so again, simple math, but there's the decoding of the storyline first. So in that last one, we started to touch back on first semester things. And here we are again, an object in a vacuum falling in a vacuum near a planet. It's got a really small mass and a really large charge. And in this region of space, there's this electrical field that's all horizontal. And then a gravitational field that's all vertical. What's the net force? Well, net force is always the sum of all the forces. And so since you have only two forces, you have a gravitational force and you have an electric force. That's all that's here. All right, so that means you have mg plus qe. That's all that's going on. So you plug and chug. 0.3 kilograms times 0.50. I guess we could put newtons per kilogram there. And then 4 times 10 to the 8 coulombs times 2 times 10 to the 7th newtons per coulomb, which means I'll get newtons plus newtons. Let's see, this works out to be 1.50 newtons plus negative 0.800 newtons. And so you just add x parts to x parts and y parts to y parts and z parts to z parts. So in the end, you'll get a negative 0.8, a 1.5, and a 0 newton. So just to be clear, x parts getting added, y parts getting added, z parts getting added. And that would be it. A little bit more in the horizontal than it is vertical, but that's the net force on the object. If we wanted to, what would be the angle? Well, the angle is always going to be with vectors, the inverse tangent of the y part over the x part. So we could have the y component and the x component. That would give us an angle, nothing flat. And, square root of sum of squares gives us the magnitude. All right, but better to do it on a calculator. All right, this next problem. This is another one where if you have the old version of the handout, there are signs missing. So I think everything was positive in that one, and there are 5 negative signs. All but the first x term are actually negative. So take a moment to adjust your handout if that's the case. And so this problem goes on for, I don't know, 4 or 5 pages. And we're just breaking out the procedure because one of the things you got to do, there's an interaction that's happening at some distance. And there's an observation location and there's a source location. And you need a position vector so that you can get the magnitude and the direction. Because you'll notice in these laws, you have the square of the magnitude of the position vector in the denominator, and you have the unit vector times all of that, the whole thing. And so you must know that position vector. You have 2 position vectors, a here and a there, and then there's a relative position vector, the difference between them. And it's observation minus source, because the observation location is the end point. All right. So this is really simple. The source location, you could call it particle or source, is just going to be that second thing, and then the observation location is just going to be that other one, 0.5, negative 0.1, negative 0.5. Easy peasy, but just the process of recognizing what is it that I'm dealing with. If you swap those, you're going to have the wrong pointer, and hopefully nobody's relying on that for navigation. All right, continuing on. Part C, what is the vector that points from source to observation location? Well, we like to use R, you might remember, and S for position labels, because P was used for momentum and stuff. So this is going to be R observation minus R source. I'll just leave it that way. And so we're going to have that first vector minus that second vector. It's meters. And so again, how does this work? It's parts to parts. You're going to subtract x parts, then you're going to subtract y parts, and then you're going to subtract the z parts. And so R, the resultant vector, if you will, would just be 1.1, because a 0.5 minus a negative 0.6 is a plus, and then 0.6 and negative 0.3 meters. Yeah. So there we have our R vector. Nothing particularly difficult about that. So I'm just chunking this out so that we think about these easy steps in a serial fashion, and then we're gonna, what's the magnitude of R? Well, technically, you'd write it this way. So we had a 1.1 for that x component, we had 0.6 for that one for y, and we had a negative 0.3 squared for that one, and so you get 1.29 out of that. Again, nothing special. I'm not expecting that you'll do all of this by hand. I'm hoping you have the mag and the norm button on your calculator figured out, or you have some sort of computational device that just does it for you. I see no reason for calculus students to do this kind of work by hand. You might need to do some other things by hand, and I'll try to alert you to that and move forward. So now we want the direction of the vectors, or we want the unit vector, otherwise known as that. And if we do the inputs to them, I'm just going to give the answer here because it's just dividing the parts of the original vector by its own magnitude. And so that's our unit vector, our unitless unit vector. Unit in terms of, it's thinking of numbers as units, which is, I don't like it a bit, but the people who thought of that, men who wore wigs and tights, they're all dead now. Okay. Here's another problem that has a, not a particularly complicated, but it is a tedious setup so that you can do the math. So I want to give you the bulk of that, and then we'll just do the math here. So helium nucleus, which has 2 protons and 2 neutrons, and then a proton. So big helium nucleus on the left, proton on the right. And we want to where is the electric field 0? Well, it's at location X, and that's necessarily going to be closer to the proton because the nucleus has double the field. So it's going to, where those fields overlap to 0 or meet up at 0 has got to be somewhere in between them, but closer to the smaller charge. Okay? If they were opposite charge, it couldn't be between them. It's physically impossible. We'll actually address that more. You should think about that before we get to addressing that in sometime next week probably. Explain briefly but carefully and use diagrams to help in the explanation. So, and then we're going to be quantitative about, so the qualitative explanation is what you see on the screen there. So I got that little grayed out thing, sketch the nucleus along the x-axis. Place X, we'll make X the origin, that's our 0 point. Nucleus to the left. And so the position for helium is 10 to the minus 10th. I didn't get that raised there. And so how do we get quantitative about the relative distances? Because we know, according to the problem, this distance and that distance, angstrom basically. I think 10 to the minus 10th is an angstrom, if I remember right. Now, let's do some math here. So we're looking at the magnitude of the helium field equaling the magnitude of the proton's field. That's what the diagram is saying. That's what the question is addressing. And so here, if we just apply the formulas, we're going to have the charge of the helium over that distance of the helium squared has to be equal to K times the charge of the proton over the distance of the proton squared. Happens to be the case that the charge on the helium is just 2 times the charge on the proton because it has 2 protons. All right? So we can take that away, and we could just write 2 QP there. Well, nice thing. The K's drop out. The charge on the proton drops out. And you have a fairly nice, simple equation here where that proton distance squared that we don't know the value of is just equal to the helium distance squared, which you do know, over 2. So that means if we do that math, we end up getting 7.07 times 10 to the minus 11th meters. Easy peasy. And then continuing, so almost the same narrative, except now we're talking about an electron instead of a proton. And so the 0 point is outside of that system, not within it, where it gets balanced out. And really nothing changes here except the sign, because we're not changing the magnitude of anything, we're changing the direction. Okay? And so you could kind of reason that way towards that answer. And so that explanation is given. I'm going to move on for the sake of time. All right. This problem here, you could set this up in the PHY simulator. In fact, we'll do that here in a little bit, but I want to get at the math first. So find the electric field. Oh, make sure that your charges match. Q1 should be a negative and Q3 should be a negative. I think the original didn't have that on it. So what do we need? We need R. Oops. And R is going to be that R observation minus R source. And if we're talking about Q3 due to Q1, we're talking about this right here. So what's that going to be? Well, if you look at this, each square is a centimeter. So the top two are 3 centimeters up from the bottom row, and the two on the right are 4 centimeters horizontally away. So you're going to have a 0.04 0, 0 for the observation location, and then the source location will be 0.03, 0. And that means your resultant vector, for the position vector for that, pretty much just that. So meaning you're going to go over 4 and down 3. You could also just think of it that way. I'll spare you the algebra, but the magnitude of R is going to be 0.05. That shouldn't be surprising since you have a 3, 4, 5 triangle. And the unit vector, if you divide the magnitude of the resultant by, or the resultant by its magnitude, you get 0.8 and negative 0.6, yes. So these problems, you need to go through this. What's the position vector? Because that's going to be the line of action that the forces and the fields act upon. And then I'm going to need magnitude and direction because we're dealing with vectors. So that's really simple. So people look at this and go, oh, it's tedious, it's arithmetic. Just ripping the features off of the geometry and doing some arithmetic on it. All right. So now that we have that piece of information, we can compute the electric field, which is going to be K times Q, when it's going to be Q1 in this case, over that distance, the square of the magnitude of that distance, and we would have that unit vector in it. So we're looking at a magnitude and a direction. Vectors must have a magnitude and direction. So when you see these formulas, those are the kinds of things you need to see and think. Because if you're ever going to use them, and especially code for them in systems, which you're going to code for things because you're going to be engineers and scientists, and there's no escaping that. you need to know what you're dealing with. All right, so basically, we're going to have 9 times 10 to the ninth for that constant. We're going to have Q1 was a minus 4 times 10 to the minus 6, that 0.05 squared, and then I'll just put r hat in there just for simplicity. And that means in the end, you crunch all of that numbers, all of them numbers, 1.15 times 10 to the 7th, 8.64 times 10 to the 6th, 0, and that's going to be newtons per coulomb, or volts per meter, depending on the system. So we computed it. Find the electric field at the location of Q3 due to Q1, which means finding the right position vector, relative position vector, which is in the top 2 rows there, and then we use the magnitude and direction to finish the deal on this vector quantity. All right. Part B, find the electric field at Q3 due to Q2. All right, so we're in that lane there. And so since this is all one direction, we can just go straight at it. All right, we're going to have K, that's a lousy K, Q per R squared. Just assume that it's all magnitude there, so 9 times 10 to the ninth for that constant. And we have a positive 3 times 10 to the minus 6, that's what a microcoulomb is. And then that r squared distance, well, this is going to be 0.03 meters squared, because it's 1, 2, 3 blocks up, and they're all 1 centimeter, or 0.01 meters. And we could put 0, 1, 0 for the unit vector, and we probably should in that regard, but we can write, we know that it's in the y direction, so we know that E is going to be 3 times 10 to the 7th, if you do the number crunching, newtons per coulomb. Okay. Oh, let's see. Think that find the electric field at the location of Q3 due to Q2. So due to Q2 is down, okay? And so due to Q2 would have to be down, which means this is negative. And so see how easy it is to, you'd have everything right, that magnitude's the right magnitude, but the sign was wrong initially. So take note of that, like come back and think about this later. Be a small error from a math standpoint. So on a test it wouldn't be a big deal, but if you screwed that up in real life, that's why we simulate the heck out of everything to make sure nobody made silly math errors. So, math errors cost you something in your academic life. They'll cost you a lot in your professional life, but you're more likely to not put into production a math error because you have a humongous team that's checking and double checking. You simulate the heck out of everything, and everybody knows it conforms to reality. Everybody's checked and double checked each other, and so you're not likely to translate a mistake like this to a product, to a spaceship or rocket or whatever, and kill everybody, or fail to save the world when it was your turn. All right, so this one, find the net electric field. Well, the net electric field, the net anything, it's always the sum of that thing. So you have E1 plus E, I'm gonna run out of room if I do all that. Sum of the two electric fields. And so we had negative 1.15 times 10 to the 7th, 8.64 times 10 to the 6th, and we had 0, negative 3 times 10 to the 7th is 0. And so when you sort all of that out, nothing changes on the x scale, but you get a little bit of combination on the y scale. So, again, easy math, but you need to pay attention to the details, which is why we're going over them. It's easy to mess this stuff up. All right, where do you find the net force on Q3? All right, the net force on Q3 is going to be Q3 times that electric field. Now that we know what the electric field is at the location where Q3 is, because we haven't used the charge on Q3 yet. We've just, what would be true at that location? All right, so here we're going to do minus 2 times 10 to the minus 6 coulombs. And then that E net, which I'm not going to write it out in that space. It's just what we had on the other screen there. And so you're going to get 2342.60 newtons in this case. So, because basically you have a micro multiplied to a 10 million thing. So it's going to bring it down to the tens level. And those are significant forces for something that small. All right, we're continuing with this situation, but now we're going to pay attention to the empty observation location for this thing here. And so I want to switch momentarily. So continuing here, what is this problem? Find the electric field at A due to Q1. So we're talking about this lane right here. So again, E, the magnitude of that field of E1, and one way to write magnitude is just drop the bars and the arrows and just write it. It's going to be K Q over that R squared, whatever R squared ends up being. So 9 times 10 to the 9th for that K value. Q1 is a minus 4 times 10 to the minus 6 coulombs. And that distance looks to be a 0.03 that gets squared, meters squared. This has units here of Newton meter squared per coulomb squared, by the way. So E1 just going to end up being 4 times 10 to the 7th newtons per coulomb. That's an easy calculation. For the next one, I went ahead and left the math from before because it's not going to change. It's this right here. We've already no point in writing all of that again. So E2, again, K Q2 over its R squared. So 9 times 10 to the 9th. Q2 is a 3 times 10 to the minus 6 coulombs. And what was this? 0.05 meters squared. And we could put R hat here. It's almost the same math up here. I think this was a positive before, but same numbers. Signs work out a little bit. And so in the end, E2, what's it going to be? Negative 8.64 times 10 to the 6th, negative 6.48 times 10 to the 6th, nothing in Z, newtons per coulomb. So not difficult math, but minimally tedious. All right, doing good for time looks like. We'll actually get done early. That's good, or we'll certainly not be late. find the electric field at location A due to Q3. This is another easy peasy one because it's all one direction, not to be confused with the band. So if we plug and chug all of that, and I'll spare you, you get a magnitude of 1.125 times 10 to the 7th newtons per coulomb, which means as a vector, since it's all x, you would 1.125 times 10 to the 7th, 0. So we can do things in magnitude and then step back and go, okay, this is all one direction, so let's put it into vector form with zeros for the other thing, okay? And now, what's the net electric field at location A? So the net electric field would be E1 plus E2 plus E3. We would add all of those values. And I make sure I have them here. So E1 was no x, but a 4 times 10 to the 7th. E2 was the long one, 8.64 10 to the 6, negative 6.48 10 to the 6, 0. And the one we just did was 1.125 times 10 to the 7th, 0. And if you crunch all of that out, and I didn't. I didn't print that page. I'm sure I crunched it out, just didn't print the page off. So we would just add those numbers, and I'll just, that's just addition, so I'm not gonna labor that one, so 0 plus that, those x parts, and then this y part, plus that y part, plus 0, and then you have 3 zeros at the end. So I'll do the hard one, 0 at the end, and you guys can do the easy stuff. Ha-ha. Ha-ha. So that is the handout. We are done with this handout.